Hi everyone. So I have here two Ecoflow Delta Pro units, which are very large battery inverter systems that can charge from solar power. And some people like them for being off-grid or for backup power. And I don't necessarily endorse this particular brand. This is just what I ended up with. But in any event, it has AC outputs that can replace the power in my home if the power goes out. And the point of having two of these is that each of these is just 120 volts. But if you connect them through this awkwardly angled set of cables, there's something called the double voltage hub that joins the two of them, synchronizes them, and gives you 240 volts in case you need to power any 240 volt loads. Now, we've been using this for a while, and one of the things that's been nagging at me is that the thing we're using this for is to run a well pump. So it's charging from solar power each day, and the inverter is running continuously, generating 120 volts on each leg that turns into 240 volts at the double voltage hub because it's a 240 volt well pump. Now, there is an energy cost associated with running the inverter whether or not there's a load, and that's about 35 watts per inverter. And I've got two of them, so I've got about 70 watts getting burned 24 hours a day, 7 days a week to power a well pump that just kicks on for maybe a minute at a time during the, several times during the course of the day. That is tremendously inefficient. I'm pretty sure that we've been burning up as much energy on the inverters being on standby as we have actually powering the well pump. And I'd like to do something about that. Now, newer models, there is a Delta Pro 3, whereas this is just the original Delta Pro. The Delta Pro 3, and I believe the Delta Pro Ultimate, have a feature where the inverter only kicks on occasionally to check to see if there's a load. And if there is, then it switches on into full and powers that load until it goes away. And that is supposed to save a fair amount of energy, but you're still running the inverter intermittently, and I don't have good data on how often it runs, and certainly they wouldn't let me adjust it through any user interface that I've got. So there's a delay associated with that. How often does it fire up the inverter to check to see if there's a load there? And if it's not often enough, then the pressure in our well tank would drop, and that would be a problem. So I don't know for a fact whether the Delta Pro 3 or the Delta Pro Ultimate would actually solve the problem to my satisfaction. But I've already got these hideously expensive units, so I'm not going to be buying a new one anytime soon. So I'm thinking, can we kind of fake it? And I am aware that there is a software API that Ecoflow puts out for talking to these. I think over HTTP, maybe Bluetooth is involved. I couldn't really figure out the details, and I kind of gave up because I couldn't figure out whether it would just let me turn each individual unit on and off, or if it would actually turn the double voltage hub on and off through that interface. And really, in a grid down situation, I don't want to be trying to maintain some kind of network connection to these things. I just want to be able to turn it on and off. So my plan is to see if we can, and this unit has a little push button on the back that you can't see here, that turns it on and off. My thinking is maybe we can get inside of this thing to the circuitry that is associated with that push button that turns it on and off, and use a microcontroller to turn it on and off when we want it on and off. And then we just have to figure out how to determine when the well pump is trying to run and turn it on at that point. So that's the plan. So underneath each of the 4 rubber feet here, there is a screw inside that hole. So I had to pry up each of the 4 rubber feet at sort of the interior side of those feet to get to those screw holes. I thought there might be another screw here underneath the label, but that turned out to just be a dimple. So it's just those 4 screws, and then stick in a spudger along the edge to pry it open. And here we have the insides of the device. And unfortunately, I don't think I'm going to be able to get this PCB out of the casing in order to really get a good look at what's going on. I'm not entirely sure how they assembled that. It looks like there's a metal strap on either side of the L1430 receptacle that might be holding that receptacle to the front of the housing. And so I'm thinking they might have secured the innards of the receptacles to the front face and then placed this circuit board on top and soldered it at all those different points. So it would not be practical for me to get it open further. So I think we'll have to leave the disassembly at that, but it doesn't look terribly complicated from what we can see in here. So on each side, there's an input there and there for the input from each of the 2 Delta Pro units. And you see a white box on each side that looks like a relay, presumably so that they can only, this system will just enable power to the receptacles. This is the L1430 receptacle, the round twist lock one. And then the 2 more conventional 240 volts that don't have the twist and don't provide a neutral are on this side. And so presumably those relays are used to only power the outlets when power is present from both of the Delta Pro units, so you don't get into a scenario where one leg is powered and one leg is not, which might be kind of weird. I don't know if you could break something that way, but probably equipment was not designed expecting power might be present on only one leg. On the other side, this is the power button, and there's a little logic board in there that I assume has all of the smarts of this thing. The little wires coming through the thick cables go off here to this logic board, and the really thick power carrying wires, of course, get soldered onto the PCB itself. And they've got these really thick traces that I guess are beefy enough to handle 30 amps, because that's the output of this thing. So what I would like to do, and I may have to cut away some of this housing to make it happen, is to get at that black push button there, and ideally the LED next to it, because that lights up when the unit's on, so I could get a confirmation signal of whether it's on or off. And then since I can't really get a good look at the traces leading to the relays and how the receptacles are connected, I think what I'm going to have to do is get a generator cord that I can cut in half so that I can get the sensing, because I want to see whether there's a load across this and these 2 connectors. And to do that, I'd like to be able to switch the load between power and a sensing line so I can check for continuity. And I doubt there's anything clever I could do if I could get the front housing off, but since I can't get the front housing off, I think I'm definitely going to have to just get another generator cord that I don't mind cutting so that I can put the sensing in there. Alright, so that took a bit of doing, but I managed to cut off the region with the power button so that I can get to the logic board behind it. And so again, this is the power button that I'm hoping to wire into based on its contacts, and that LED that I'd ideally like to get a little wire onto each side of. Maybe remove the LED, I don't need it anymore, just so I can sense whether it's on or off. And now we have a little bit of a better look at the circuit board with hopefully enough access to do that. I still can't read anything off of this chip. I think they may have deliberately obscured the markings, not wanting us to know what's in there. Or maybe it's just a coating of some kind to protect it. And now that I'm getting up close with it, yeah, I think there's a coating over this entire board, which unfortunately is going to make it more difficult for me to do what I was hoping to do. I might have to smash this switch open to get at a metal contact on the inside, and I might have to just settle for gluing a photocoupler or a photo sensor on top of the LED to sense whether it's on or off. So of course this is not going quite as well as I'd hoped, but hopefully still salvageable. And I ended up putting on a mask while I was cutting this because it was making so many tiny, tiny little pieces of plastic that I felt like I was breathing all of that in. So, with a wire going to what looked like the correct contacts of the switch, the question becomes, if I short these two wires together, does it turn on? Hey, it worked. I guess you can't really see that, but the light turned on. If I short the wires again, it should turn off. Okay. So the next question becomes, can I use an optocoupler in lieu of actually shorting those wires together in order to get it to turn on? And this doesn't really matter in that I can use a relay if I need to, but it would be simpler if an optocoupler could accomplish it. So let's see what happens. Interesting, it sort of blinked, but it didn't actually turn on. Oh, it just had to be momentary. Okay. So if I can do it momentarily again. Yeah. Okay, perfect. So I can just use this simple little optocoupler in lieu of a relay for shorting these two wires together to simulate a button push. I just have to make sure that the pulse is quick enough that it gets interpreted as an actual button push. And if you're not familiar with an optocoupler, the way this works is basically on the left side here, we have an LED embedded inside it. And so when I run power through it, through this resistor, that triggers a little light internally. And then on this side is a photo transistor, so that activates when there's light coming from this side and sort of effectively shorts the two pins together more or less. And so that completely decouples the two sides. So my Arduino circuit on one side won't be in electrical contact with any of the Ecoflow circuitry on the other, because it's just a beam of light traveling between the two.
And I already wasn't liking the idea of trying to wire into that LED there for my status information, and the fact that I'm not going to be isolated from the power supply running this just makes it an even worse idea. So I think instead I will go directly to the two hot wires and just sense whether there's an AC voltage there. Also, this LED, it pulses slowly if it's connected to one of the two Delta Pro units that it needs in order to function. So it's actually not a perfect indicator of on versus off. There's that third pulsing state also, which is sort of a variant on off.
So this is the board that I came up with, and I always think, oh, this will be quick and easy, so I'll just do it on perf board, and of course it always turns out to be a bit of a mess. In this case, I put some back-to-back diodes to try to protect against kickback from the motor when we switch it over to load detection. If it happens to have been running and powered at that moment, then motors are inductive, and so there could be a fair amount of current wanting to flow, and I'm hoping those back-to-back diodes will help prevent that. Of course, after I recorded that, I realized that I had used the wrong diodes on this board, and trying to get them off was a pain, and swapped them out. And so this is a bit of an aside, but I've decided that these little prototyping boards are really a pain. They've only got the copper on one side, so you can't come in from the top if you decide that you need to get a wire in from that direction. And you're manually making every connection, you know, folding legs over, soldering between pads to bridge things, trying to do everything yourself. And it's just such a pain. And I've got a number of these cheap little boards. And, you know, you can make it work, but it's really annoying. And I know there are some slightly more expensive ones where there are copper pads on both sides. But really, I don't know why anyone would bother. I guess if you've got a lot of really little components and are really trying to pack it in, but without any of the pads being connected to each other, you're doing everything yourself, and it's an incredible pain. So I think what I probably should have been using all along is called strip board, where they have strips, and this is commonly used for prototyping. It's really not as common, at least there's not as many listings on AliExpress for stuff like this, and it is only on one side, the copper, but that's because these strips are running the full length of the board, and you might have to cut them in a few places in order to make your layout work. So I think this is probably a more sanity-saving way of doing it. But the more I thought about it, the more I thought, you know, I do a lot of microcontroller projects, and I always end up connecting a microcontroller, be it an STM32 Blue Pill or an Arduino Nano or what have you, to whatever it is I'm doing. And wouldn't it be nice if I had a board that sort of had those basics sorted out for me? So I actually decided to get my own little prototyping board printed, and so this is my custom prototyping board, where there's a spot here for a microcontroller, and these pads are connected where there's a white line between them. The pads are connected, so you can use it more like a breadboard and solder in at multiple points without having to make all the little connections yourself. And I even put some little solder pads in here so that we can bridge the power and ground from the microcontroller onto these rails that I put at various locations on the board. So I tried to make my life as easy as possible. And there's space here that is laid out for connectors I could conceivably want to use, room for surface mount parts if I ever need to mount surface mount parts. But I think that on the whole, this is going to make my life significantly easier. And I found out you can get little standoffs with adhesive pads on the bottom. So on the whole, I think that this is gonna work out better. And I'll put a link down below, I guess, if you want to get your hands on a board like this. But I think that's going to make life easier. So you can see here, I put a connector here for the control of the relay, turning it on and off and giving it power. Voltage detection is over here. This is where I'm using an optocoupler to determine whether there's any voltage on the line. That optocoupler, so there's a voltage divider from the inputs that's located near the relay board, and then the divided voltage is coming down here to power the LED. It's inside of that optocoupler, and then on the other side it'll go to either 0 or 3.3 volts, and it's low pass filtered because 60 hertz AC, and I wanted just an on or off for my microcontroller, so that goes back. This is for load detection, so that's where I put 5 volts across the line to see if the pump is physically connected, which means that it wants to run. And I have, these are the Zener diodes that I should have installed the first time to make sure the voltage doesn't become excessive. Now this is never touching AC, but if there's some sort of capacitance or inductance in the load, then hopefully this will dissipate it. And I decided to, since things are laid out neatly now and I have room to work, I added some Schottky diodes for both the load detection and the voltage detection, so that it doesn't exceed the 0 to 3.3 volt range by more than the Schottky voltage, which I think is about 0.3 volts. So on the whole, this should work out a lot better. Okay, so in hindsight, this should have been obvious, but those Zener diodes that I put to protect in case there was a little bit of back EMF, they have completely shorted out. I think it switched when the load was going, and there's more than a little bit of back EMF. This is a giant motor, so we need to change the plan here. So instead of that, I'm bringing out again the giant resistors, the 2 ohm resistors, and so this puts a 1 megohm resistor in series with those 2 lines on which I'm trying to detect continuity and may have back EMF. And then each of those has 100K going to ground and 5 volts respectively. So on this end, I'll get about 2.5 volts when this megohm resistor is shorted out. So when there is a load present, and I'll get close to 0, I think a 1/4 volt or something going back off to the Arduino when there is not a load detected. So hopefully we'll fare better here with the big high value resistors. Again, we're not connecting directly to mains voltage with this, but we are connecting to a motor that may have just been abruptly disconnected from mains voltage. So we won't get any sustained mains voltage, but we may get what is it, 300 volts peak if we disconnect it at right just the wrong moment. So hopefully these resistors are high enough value and high enough wattage that we won't be frying any more components. I was trying to ponder the question of whether there's a good way to use an optocoupler to do this in order to sense continuity on a line that may have high voltage present, but I couldn't really think of a good way of doing that. Let me know in the comments if you know a good way of doing that, but I'm hoping that really big resistors will do the trick. They tend to work well in multimeters, so I'm hoping they'll work here too. This is what the pressure switch for a well pump looks like. So the wires would come in through these holes on either side, and one wire from the 240 volt incoming power would go on this side, and one wire would go on this side, and then similarly one wire to go to the pump itself would go on this side, and one would go on this side. And when there's enough pressure coming up the pipe into it, that forces this plate back so those contacts don't touch each other, but once the pressure drops below some threshold, they touch, they complete the circuit, and power flows to run the pump. So this simple switch mechanism is why my simple continuity detection, load detection will work. You couldn't check for demand on a refrigerator this way. This is one of the few things where it's physically disconnected when it's not trying to run, and it's physically connected when it is.
Now this is interesting. I said at the beginning of the video that the Delta Pro 3 and Delta Pro Ultra had that feature where they could not run the inverter continuously, just activate it when a load is detected. But here's a Reddit post that seems to suggest that that feature recently disappeared. So that's interesting. I wonder if some of you with the later models would have to do a hack similar to mine also. That would be kind of a shame, because cracking open the double voltage hub is scary enough. Most of you probably are not eager to crack open the actual multi-$1,000 Ecoflow unit itself. Not that you should be trying anything that you see here at home anyway, because I'm just some idiot on YouTube, and you really shouldn't be attempting to modify any of your devices. I guess that's kind of the problem with these all-in-one units, that you're very much at the mercy of the manufacturer as to what they do and don't provide.
So I think it's working now after having adjusted some timing. I had an issue where this thing was shutting it off when it wasn't done pumping yet, when there's heavy load on the well, which is not intrinsically a problem, but I don't really like cutting power to the pump to see if it's still running, to then just have to turn it back on a second later, because cycling that pump is not great. That's the whole point of having a pressure tank. So I've adjusted the timing, and I think I've got it so that it runs for longer than the maximum duration that it could reasonably take to refill the pressure tank, even when there's a fair amount of water flowing to something that's draining the tank. Long term, I don't know. It might be better instead of just running it for a couple minutes at a time. There you see the power stopped being drawn, but it's still running the inverter because it doesn't know that it's shut off. And in a short time, the timer will go off and shut it off. And then it really won't be all that long, because again, I'm under heavy water draw right now for testing purposes. It really won't be very long before it kicks back on after that. So that was it turning off. And then I think it'll only take probably another 20 seconds or so before it turns back on again, which is fine. I mean, this is a pretty decent test, I think, of the longest it could take to refill the tank and the shortest interval between demand when the pump turns back on. So intrinsically, it's not a problem, although if we're really getting a lot of well pump demand, I wonder if, for the benefit of the relays inside the Ecoflow, there it goes again, that means the pump just kicked back on. I wonder if for the benefit of the relays inside the Ecoflow, if it might be better to just run for, say, half an hour or an hour after a demand signal to try to get through any periods of high demand. But that's something I'll have to think through. I might even consider putting a current sensor on one of these lines so that I can actually sense inside the microcontroller whether current is being drawn, and then I could actually have data. It adds a little bit of complexity, but I could actually have data as to whether the load is still running or not, and then I can be pretty confident that I won't shut it off while it's running. But incidentally, I have shut it off while running, and those big resistors seem to be holding up okay. So I think we have a fully functional prototype at this point. And since I mentioned AliExpress, I should also mention that for those of you in the United States, tariffs on imports from China are going up, and most significantly, the de minimis exemption that we have historically enjoyed as consumers, just buying small amounts of stuff online from AliExpress and other sellers in China. That exemption is going away, which in and of itself is not necessarily that big of a deal. It would just mean a 30% import tariff that you would have to pay, which is in line with what other countries do. A value-added tax on an import is not unusual, but there's language floating around about a minimum of $25 rising to $50 in terms of the fee you're going to pay per package. And so if that happens, then AliExpress won't really be a viable source for electronic components like this anymore. So we'll just have to keep an eye on that. Those of us who live in the United States will have to keep an eye on that and adjust accordingly. Of course, there are plenty of vendors here in the United States that will sell you electronic components, and of course they're just getting them from China also, but they're importing them in bulk. So you're kind of just paying a middleman there, but that might change the calculus a bit. So anyway, I just wanted to put that word of warning out there so you don't have a rude awakening when you get a $50 bill when you ordered a $10 package from China. And I've got 4 more of these for my next few projects, and then I don't know what happens, because with the trade war going on, it's not going to be economical to get these printed in China or anywhere really. So this might be kind of the end of hobbyist PCB design for a while. So that's kind of sad, but we'll see what happens on that front. So just to kind of run you through the final, or what I'm going to call for now the final version of this project. I might be tweaking it in the time to come, but it works, and this is about where I landed. So it's centered around an STM32 blue pill development board for the microcontroller, the brains of the project. That connects to an optocoupler that I'm using to push the button to turn the inverter system on and off at the double voltage hub. I have load detection, which consists of of 2 big resistors connecting the load wires, which are the 2 phases, the input and output of the motor, to 5 volts and ground. And there is a 1 megohm resistor there that gets shorted out when a load is present, when the motor is joining the 2, with very little DC resistance. So when that 1 megohm resistor gets shorted out, then I know I have a load present. Over here is where I'm doing voltage detection to figure out whether the inverter is on or off. So that consists of another optocoupler, and these lines coming in here from the 2 lines of the inverter output, those already are coming by way of very large resistors that I located right at the relay board that I'm using to switch back and forth. So depending on which setting the relay is on, either the load, where the pump is, the pressure switch and the pump, is either connected to a sensing circuit, which is the load detection circuit I just described, or to the inverter itself to provide power to it. and these are 30 amp relays. So anyway, these lines already have the resistance before they come into the board, and I'm using a fairly large resistance because at 240 volts you can have a lot of power to drop even with very little current. So actually the signal to the microcontroller doesn't quite make it up to 3.3 volts. It's somewhere around 2.5, but that's good enough. I could hit 3.3 volts at higher current, but there's just no reason to dissipate more power through those big resistors over there. And then I added a buzzer here, which has actually been very useful for keeping track of what's going on, because I can have it make different sounds depending on what's happening, which is extremely useful for debugging. So it makes it very clear when it's turning on, when it's turning off. When it gets confused, I've got it to set off an alarm if it has failed after repeated attempts to turn the inverter either on or off. This header socket here, I had actually intended to use a wireless remote and receiver, thinking that it might be convenient to be able to turn this system on and off, to change modes on this system from elsewhere in the house. Although the more I thought about that, the less it made sense, because I don't want this system doing the auto detection for loads if anything other than the well pump is connected. I don't want it turning my refrigerator on and off frequently, because that's not going to be good for it. And connecting and disconnecting my refrigerator to it is going to require physically being here. So I couldn't really think of a scenario in which I would actually be wanting to change modes without having to physically reconfigure something here. But what I did kludge in on that connector is some resistors, pull up resistor and pull down, that go to some wires over here for a simple push button. And that's what I'll use when I need to switch the system between running all the time, running continuously, if say I want to run my refrigerator or whatever else, and just running on demand for the well pump. And I will say that the load detection circuit is giving me some false alarms from time to time. I'm not sure what exactly is causing that. One time it seemed to be a static discharge halfway across the basement. I happened to have been walking across some foam padding that tends to build up a static charge on me, and I touched a metal beam that supports the house, and I got myself a small static shock, and I heard this thing beep on. So I guess that could have been a coincidence, but that was awfully precise timing that I got the shock and it turned on. But I'm not very motivated to debounce this thing or anything like that, because I really do want it to start up as immediately as possible when the load gets attached, just so that I'm not putting any more stress on any of the well equipment. The pressure tank, for example, has a bladder inside of it that presumably does not like to get stretched out because it's dipped below its nominal pressure. So I prefer not to mess around with that, and if I just get the occasional false alarm, I think I can live with that. It just runs for a couple minutes and then it turns back off anyway, so not a big deal. And then, as I sort of mentioned earlier, that's the relay board behind kind of a makeshift blast shield over here, because this is the comparatively high voltage side of things, where I've got two relays that can handle 30 amps in their normally open position. And that's the Ecoflow hub here, where I've taped over the ports I'm not using, and these are the lines going into that button that I cracked open and soldered, going over to my button pusher circuit. So, oh, and the relays themselves are controlled, or the signals to control them go out here. So the microcontroller uses this connector to turn the two relays on and off in unison. So I'm just using one digital output because I want these both to flip at the same time. There's no scenario in which I want them to flip separately, so they are deliberately both wired to the same control pin. and I'm using this hefty bin as a container to try to enclose all that to make it, you know, reasonably safe, or at least less dangerous. So there we have it. That was actually a smashing success. There were a few small hiccups along the way, but it's really working quite well. Maybe I could stand to add a current sensor just to make sure that I'm really turning off the power at the right time, rather than having to disconnect it, see if there's a load, and possibly reconnect it. But on the whole, I'm pretty pleased with the way this turned out. I think it's still fair to call this a misadventure in electronics, because this is still kind of a crazy half-baked scheme that I came up with. It happens to have worked this time. So I hope you enjoyed this video, and if you did, please give it a thumbs up. Thanks.